All right, so this should be the last class of machine learning for healthcare in this semester. Didn't expect to end end the entire course by doing this online for the last time, but sounds like a reasonable compromise because it's really hard to accommodate for everyone's schedule to see like who's available on what time, what date. So this is probably for the best. All right, so today's topic would be Bert and GPT. And in order to talk about Bert and GPT, we first need to talk about the transformer model a little bit in more detail. So before, when I talked about the transformer, I was actually talking about the encoder part of the transformer. So when I say the encoder part, so we need to look at the the very first paper that introduced transformer to the world, which is attention is all you need. So that was presented back in December 2017. So it's almost like 2.5 years ago. So this paper this is the paper that introduced transformer and the self-attention that comes with it to the world, and they did it in order to perform translation. So basically sequence to sequence, from like French sentence to English sentence, or German to English, or English to German. Doesn't really matter. Basically, all what really matters is this paper was presented under the framework of sequence to sequence. So there's encoder and there's a decoder, and both encoder and decoder were implemented with transformers. So previously, when people did a neural translation, neural machine translation, they used RNN for both parts. They use RNN for the encoder, they use the RNN for the decoder, and the only difference in this paper is that both parts, both encoder and decoder, are now transformers. And there are subtle differences between the transformer and the encoder, and transformer as an encoder and transformer as a decoder. So we'll talk about that first because it is important. We need to talk about this because Bert is only using the encoder part of this paper, and GPT is only using the decoder part of this paper, which is kind of interesting actually. They are two very well-known pre-training methods, and one is only using the encoder part and the other is only using the decoder part, which is kind of interesting to me actually. Anyway, so 2 classes ago, I talked about when I was talking about the transformer and the QKV operations and all the self-attention and all that, I was only talking about the encoder part. So since we're already familiar with it, I kind of skipped over the positional encoding, this part, because mainly without the positional encoding, then what transformer models is actually a set of tokens, not a sequence of tokens. I think I've already mentioned this before. So transformer without the positional encoding, without explicitly telling the model which token comes before which, like others, like when we have like you are a good boy, then we need to tell the model that U comes before R, and R comes before A comes before a good, A comes before good, and such and such. So we need to tell the model that there is a sequence, or there's an order embedded into the tokens. But without the positional encoding, then to a transformer or to the self-attention module, everything is unordered. So everything is just attending to every other tokens. So basically, when I was making connection between the self-attention and the graph neural networks, both were assuming, like transformer was assuming that all the tokens were fully connected to everything else, and it's just data in a data-driven fashion. It's learning the edge weight or edge strength as it goes. And the graph neural networks, graph neural networks, the adjacency matrix is already fixed. So that's the other end of the spectrum. So again, without the positional encoding, there's no way for the transformer or the self-attention to know that the given tokens have a sequence or orders. So we need positional encoding. And I skipped it over. I just merely said that the positional encode, in order to tell the model which, like, the order of the tokens, we somehow use the sine function and the cosine functions, But again, I'm not going to go into detail. If you're interested in that, you can actually go to this blog here, which is called the Illustrated Transformer, which is a very good blog. It illustrates, basically, it visualizes how the operations, the self-attention operations and the positional encoding, all that, like it visualizes the entire operation. It's very intuitive. It really helps you understand the inner workings of transformer. And I think somewhere here there's, yeah, here there's the like the visualization of the positional encoding. So you can, like, each row is a positional embedding. So like first row, this is like I am a good boy, whatever, and there's like a clear a division between the left half and the right half, because the left half is, I think it was embedded using sine function, the right half is embedded using the cosine function, and they just concatenate it. So this entire thing becomes a positional embedding, and then you just add it to the token embedding, to the word embedding, like I or am. So basically it tells you that, like, it basically indicates the position of the given token, of the corresponding token. Anyway, so moving back to, so if you're interested in, you can go to this blog. Anyway, so that's the whole gist of positional encoding. Now we've already covered this part. So we'll talk about this part today and then move on to Bert and GPG. Right. So as a example, I'm going to assume that we are going to transform or translate a French sentence, Je suis étudiant. I think it means I am a student. There's end of sentence. We're going to translate that to I am a student. End of sentence. End of sentence. Right. So the Je suis étudiant end of sentence, the termination symbol, they will be here, like I'm sorry, excuse me. Will be here. I am no, Je suis étudiant, end of symbol. I mean end of sentence. So yeah, there's Je suis, 4 tokens fed into the encoder part, and then of course going through the multi self-attention and the feed-forward network and the layer normalization and the residual network and all that. So the output of the encoder would be the same, have the same number of tokens or embeddings as the input. And now there are 4. So it's enough to know that the number of input tokens and the number of output tokens on the encoder part are the same. Now the decoder part needs, so the difference between encoder and decoder is that encoder can process 4 tokens all at the same time, because self-attention is basically a parallel process. Unlike back in the days where encoder was implemented using the RNN. RNN is a sequential model, so Je suis étudiant end of symbol needs to be fed into the RNN to the encoder one at a time. So it's a regressive process. It's a recurrent process. It's an iterative process. So if you have 4 tokens or 4 words in your French sentence, then you need to have like 4 operations to feed or encode the French sentence into the encoder when you're using RNN. But when you're using transformer as the encoder, you don't need to do that. You can just parallel process everything and just in a one go. So you can just put the entire Je suis étudiant end of symbol at the same time simultaneously to get the 4 embedding tokens out like this. But the decoder part still is the same. It needs to generate the English sentence 1 word at a time auto-regressively. So nothing has changed. Even if we change change the decoder, moving from RNN to the transformer, you still need to generate 1 English word at a time. So that limitation is still there. So it's a limitation. I mean, there are some ways to get around that, but that's not the point of this class. So we're just going to still stick to the autoregressive process. So, oops. Give me just a second. All right. So for example, when you're auto-regressively generating one English word at a time, for example, you, there are certain limitations that you need to enforce upon the self-attention process here. I'm sorry, right here. So there are two self-attention processes in the decoder. There's one masked multi-head attention here, which only works on the input of the decoder. So the input of the decoder is actually the predicted English words. So it is just feeding its output back to itself. So the input to the decoder is actually the previous outputs of the decoder. So that masked multi-head attention is applied on its previous outputs, the decoder's output. But here in the multi-head attention here, this actually mixes the output of the decoder, the previous output of the decoder, and the output of the encoder. So it is mixing these and these at the same time to generate the next English word. So for example, let's say that so far we have generated, of course, I mean, we also need to, I mean, in the very first step, when you want to predict the English word I, you need to have like a prompt symbol that's like start of the sentence or start symbol. So like you need to have like a start symbol here, and then push that into the decoder, and then it'll prompt the decoder to generate or predict the I. And then for example, let's somehow we generated I am, and it's now time to generate student or time to predict student. And the way it works is there's the reason that is called masked self-attention is because when you're trying to predict the student here, you can't, and remember that the self-attention allows each token to look at all the other tokens. So the start token will look at itself and also look at and student. And the I token will also be able to look at itself, start, and student, so forth, so on and so forth, which actually doesn't make sense. So, for example, let's say that okay, I'm erasing these. The A here is allowed to look at itself, is allowed to attend to previous tokens, but should it be allowed to attend to the student, the future tokens? Should it be allowed? But I mean, it is unreasonable to allow for A to attend to future tokens, which is the thing that we need to actually predict. So because then if we allow A to attend to a student, or in the same sense, if we allow M to attend to A, or I to attend to M, or start to attend to I, this would be cheating, because when we're predicting student, nothing should be allowed to look into student. No previous token, no tokens here should be allowed to attend to a student, because student hasn't been predicted yet. So that would be cheating. So in order to prevent that, we use the mask operation, which basically enforces the tokens to only attend to itself or the previously predicted tokens. So A is allowed to look at itself and previous M, I, and start. M is allowed to look at itself, I, and start. I is allowed to look at itself and start is allowed to look at itself. So basically, the mask operation would be like a diagonal like mask operation. So like I am a student and I am a student. So there will be like 1, 2, 3, 4, 4. I'm actually ignoring the start token. So it will be like A would be allowed to look at itself. I mean, I would be allowed to look at itself, but not M or student. M is allowed to look at itself and I and M, but not student. A is allowed to look at A, I, am, and itself, but not student, and so on and so forth. So it'll be like a triangular mask matrix. And the way masking works is, for example, for the weights, for the attention, so in order to calculate the attention weights, there was a softmax operation at the end of the QKV operation. So QKV operation looked like Q K transpose divided by the square root of D, applying softmax times V. So softmax is what normalizes the attention, the weight strength, edge strength to make it into a probability, to make it to sum to one. So before we push these edge weights to the softmax, if we enforce this to be negative infinity, so then the corresponding weights would look like if this was like, I don't know, like 5 and 6 and 10 and like 12, then the corresponding probabilities would look like 20%, 30%, 50%, and 0. So basically, negative infinity forces the output of the softmax to be 0. So that is why we use negative infinity as the masking element. So whenever you want to like prevent something from like having a positive probability weight or probability value, you need to assign negative infinity before you push your edge weights to attention with strengths to the softmax. So basically, yeah, that's a very like technical details, but it's just worth mentioning. All right, so that's what masked multi-head attention is for. So I'm going to erase all this. All right, so I was assuming that we'll hit start, I am, and then it's time to predict student. So here we will have four input tokens. Start I, so start I am. So far we've generated these before. So and it's time to predict student. So the decoder will have as input 4 tokens, and using the masked self-attention as I just described right now, just before. So then there will be 4 tokens here. Yeah, 4 tokens. Actually, for the sake of like clarity, let's assume that it's time to predict A instead of student. So there will be 3 tokens. It's time to predict A. So far we've generated start I am and start I am. So there will be 3 tokens, 3 embedded or 3 context embeddings out of the masked self-attention. And then now these become query vectors, and they become key and value vectors. So it's the same QKV operation, but it's just that the K and V comes from the output of the encoder, but the Q comes from the output of the intermediate product of the decoder here. So, and I'm going to assume that we're not using multi-head, but we're using single head attention because it's just easier to draw a single head attention. So since we have 4 context embeddings here, there will be 4 key embeddings and 4 value embeddings. And since we have 3 query vectors, since we have three like intermediate embeddings, there will be 3 query vectors Q. So when you have the Q, K, and V and do the QKV operations in here, what you get is what do you get? You get like this is 3 by D, this is 3 by D, this is 4 by D, this is 4 by D. So 3 by D, D by 4. So 3 by, so this is Q. This is Q. This is K transpose. And then this is some scalar value here, some scalar value underneath. There's softmax. So, and then there's V, which is again 4 by D. So this entire thing becomes D for 3 by D. So the output will be a 3 by D matrix, or there is like 3 embedding vectors, or you can say that the output of the QKV operation is here. The output of the QKV operation is here is the 3 by the meaning of 3 by the matrix is that start, I, am have each of its they have their own way of mixing the output of the encoders. Here the K's and V's. So the input of the encoder, the J sui e tu diang, so J sui e tu diang termination symbol. They are mixed and they're mix and matched, and that's how you get the context embeddings here, the 4 embeddings here. And since there are 3, so far there has been 3 words, 3 predicted words from the decoder part, start, I, and M. There should be 3 different ways to mix and match these 4 encoder outputs. That's why we have 3 embeddings as the output, 3 d-dimensional embeddings as the output or the result of the QKV operations. I hope this actually is pretty clear to everybody. Okay, then you put it through a feed-forward neural network. So the 3 embeddings, the 3 d-dimensional embeddings will be put through feed-forward neural networks, and then there's like concatenation somewhere, and then so this all will be transformed into the fixed size, like maybe 1024 dimensional embeddings or 2048 dimensional embeddings or whatever, and then you put it through the linear, and then you get through the softmax, and then that's how you try to predict the next word, the vocabulary. Like, should it be like all, or should it be student, or should it be like the end of sentence symbol or whatever. All right. So that's the gist of the transformer encoder and decoder. Hope this is pretty clear. So what you should really focus on, or what should really take away, is that in the encoder part, the entire QKV operation comes entirely from its input, only from its input. So that's why there's only one self-attention. But on the decoder part, in the decoder, there are 2 self-attentions, here and here. And here, this mass self-attention is only based on the previous outputs of the decoder. But here in the second self-attention, the Q is coming from the previous output of the decoder, but the K's and V's are coming from the output of the encoder. So there are 2 self-attentions, right? So hope this is clear. I mean, well, in the GPT, it's a little bit different, but still, like, the masked self-attention is what really matters, because in the GPT, what they're doing is basically just language modeling. So, all right. So let's move on to a Bert then. Or should we actually talk about GPT first? Let me see. Actually, historically, GPT, so there are 3 GPTs. Actually, let me just erase all of this. All right, historically, there are 3 GPTs. The first GPT, of course, is GPT-1, and there's GPT-2, and then there's GPT-3. And GPT-3 was announced, I don't know, like 3 weeks ago, I think. GPT-2 was announced sometime last year, and then GPT-1 was announced sometime in 2018. But the interesting thing is GPT-1 was announced before Bert. So timeline-wise, there was GPT-1, then there was Bert, then there's GPT-2, and then there's GPT-3. And in between here, there were a lot of Bert variants, like Roberta, Albert, Reformer, XLNet, like tons of Bert variants. But the important thing is, well, not important, but the interesting thing is GPT-1 came out before Bert. So let's just follow the footsteps of this sequence of events. Actually, that would be more interesting. How many? I forgot how long I've been talking about. I mean, how long I've been talking to myself. I think I've talked about a good 30 minutes. All right. I think I have enough time to talk about the GPT-1, Bert, and GPT-2 and 3. All right, so GPT-1, the title is Improving Language Understanding by Generative Pre-training. So I think even before GPT-1, there was something called ELMO, or I mean, pre-training. It's a pretty old concept, right? So yeah, pre-training is a pretty old concept. Like word2vec is a pre-training, and language modeling is pre-training. I mean, but I think what really differentiates, starting from GPT-1, not GPT-1 actually, GPT-2, GPT-1 was how many parameters did it use actually? Yeah, not that much. I don't think so. Yeah. So what really sets GPT-2 and 3 apart from all the other pre-training methods is gigantic number of parameters. Even I mean, GPT-3 is using how many? I think 175 billion parameters. So in Korean, that would be 1750억, which is just beyond imagination. I'm not sure how big Bert is actually. Let me take a look at it. Right here. So Bert base is using 110 million parameters, which is about Enoch. And Bert large is using 340 million parameters. So about 3억 4천. Yes. 340 million parameters, which is already large to begin with. But GPT-2 is using 1.5 billion or something, or let me see. I'm not really sure. Yeah, so 1.5 billion. So that's 15억. Yeah, 1.5 billion 15억. But GPT-3 is actually it's just pushing the step even further. It's using 175 billion. It's like 100 times larger than GPT-2. So that's what really sets GPT series apart from all the other pre-training models. It's just gigantic number of parameters, and that's what makes all the difference in the world actually, which is really interesting. All right, back to GPT-1 anyway. Sorry, back to GPT-1. So as I said, GPT-1 is a language modeler. It's just basically pre-training using language modeling. So what language modeling is basically just given a sequence of tokens or given a sequence of words, you're just trying to predict what word will come next. For example, sorry. Let's say that I have a sentence. I have a cat and a something. So given all these, given like the word, like first, let's just say word 1, word 2, word 3, word 4, word 5, word 6, word 7. What would come in the word 7? Basically, that's what language modeling is. So that's this estimating the probability that W7. What is W7 given W6, W5, W4, all the way to W1? And this is, you can generalize. Basically, it's just, yeah, this is a bad writing. Wn given Wn minus 1 all the way to W like 1, basically. So that's language modeling. And if you're using bigram, then basically you're just limiting the language model span to just the previous word, like given what comes next, which is a very very hard test. There's like million things that can come after but if you start expanding the span, the range of the language model, like to like previous 2 words, previous 3 words, previous 4 words, previous 5 words, previous 6 words, like if you start increasing the span, then it's pretty obvious that W7, the identity of W7 is very likely to be a dog. Actually, yeah, a typo. Should be a dog, right? Because cat and a dog, right? So there's a very strong association between cat and a dog. So that's basically what language modeling is. And you can do this with, of course, you can do this with RNN. Like you can feed I to the RNN, have to the RNN, A to the RNN, cat to the RNN, and RNN, like this would be like a hidden layer 1, hidden layer 2, like, I mean, time step wise, H4, H5, H6. And then given H6, you can put this, you can put H6 to through a softmax function, try to predict what word out of like 10,000 words or like 100,000 words or dictionary, what would come next in W7. And likely it would be like softmax output would be like dog as the first choice, like 0.5% or whatever. So that you can do this with RNN, but you can, of course, anything can be used for language modeling, even like just, probability models. You can do this with RNN, but you can also replace RNN with a transformer decoder. And I'm saying decoder because basically we're doing this auto-regressively. Because given I, what would come next? Have. Given I and have, what would come next? A. Given I have A, what would come next? Cat. So it is a auto-regressive, it's an iterative process. So you want to use masked self-attention. You cannot let I attend to have, because have is something in the future. So it should be, in the same sense, it should always look to itself and the past previous tokens. So I have looking at itself and I, A looking at itself and have and I, cat looking at itself and A and have and I, something like that. Basically, it's the same principle. So that is why, I mean, transformer is a way more powerful model than an RNN, because RNN has a strong inductive bias. RNN is innately used, it is constructed, or RNN is constructed to model sequences and nothing else. It is innately a sequence model, but transformers, as I said, is a set modeler. Without the positional encoding, there's no way to tell that the given set of tokens have an order in itself. So that's why you need to put position that's why you need to add the positional embeddings to each tokens. So transformers or self-attention is a way more general model compared to like RNNs. And I mean, there's a trade-off. Like, it's a more general model, so it's harder to train, but it'll adapt better when you have like humongous, gigantic volume data. Anyway, so that's why in this paper, in this GPT-1 paper, they're using transformer instead of RNN, and they're using transformer decoder to be specific. So let's look at the architecture, which is really, really simple. So there's a text and positional embedding. So there's word, the tokens, and the position embeddings, this using the sine and cosine functions. There's masked self-attention, and this multi-head attention. And then there's layer norm. There's NLP component, and then there's layer norm, and then you have the prediction layer. So note that even though this follows the decoder structure, because it's using masked self-attention, there's only one self-attention component compared to here. In the original transformer paper, there were two self-attention, because in the decoder it needed to mix the previous outputs of itself and the outputs of the encoder. So that's why it had two self-attention components. But in GPT, I'm going to erase this. In GPT, it doesn't need to mix from, there's no encoder. It is just language modeling. It is just using one sentence and trying to predict, like iteratively, just looking at one word at a time, trying to predict the next word. So it only needs to work on that sentence. So you don't need to mix and match two sentences. It's not like there are French sentence and English sentence and you need to mix them together. You only have you only have one sentence and you're just repeatedly trying to predict next word at one at a time. So that's why you only need one self-attention component here with the masked operation. Simple, right? So you do that and you just, you know, go through like millions and millions of sentences to perform the language modeling. And then what they do is after they've done that, they take that gigantic language model, the transformer-based language model, and then apply it to various tasks, such as they're applying their tasks to COLA dataset, SST2 data, which are part of the GLUE datasets actually. MRPC, I'm not sure what MRPC is. Microsoft Paraphrase Corpus. Anyway, so yeah, bunch of a lot of tasks, but not as, you know, not as extensive or comprehensive as Bert, because they were using Glue and Squad and all that. I think here they're mostly just like subpart of Glue datasets. Anyway, so yeah. So I mean, there's nothing too interesting here. It's basically like after they've done humongous pre-training with the language model objective function using gigantic transformer. I think they were using 12 blocks of transformer. I mean, 12 blocks of self-attention. Yeah, 12 blocks here, 12 blocks. So it's a pretty heavy model to begin with. And yeah, after they pre-trained it and then fine-tuned it on various like classification tasks or semantic similarity tasks, they were outperforming. They were outperforming like previous like state of the art or whatever. So that is GPT-1, and now let's move on to Bert actually, which is a bit more interesting. So Bert comes after GPT. You can see that it is citing GPT. So Bert comes after GPT, and there's a architecture here, which is basically using the transformer encoder only. And the way that they claim that their Bert is a better model than GPT or like Elmo, which is a using bidirectional RNN, I think, bidirectional LSTM. The way that the claim that they make that Bert is a better model than those two is because Bert is a bidirectional model. Like GPT was language model, so it only moves from left to right. Like there's a sentence like I have a cat and a dog, then you use I to predict am, and then you use I am. No, I'm sorry. You use I to predict have, then you use I have to predict cat, and you use I have cat to predict and, something like that. Like it only moves like one way, so left to right. But Bert is a bidirectional model. There's no I mean, GPT was a language model, and that's why it needed to use masked self-attention. But Bert doesn't have that kind of restriction. What it does is, let me see. Let me just quickly draw the gist of it, because right. So let's say that I have. Okay, this is a bad writing. I have a cat and a dog. End of symbol. End of sentence. Right. So you put this, So the way Bert works is, I think everybody, a lot of people are already familiar with this, but they use something called masked language model, MLM, which is kind of a new thing actually. So what they do is they randomly mask a subset, a certain number of tokens in the input sentence. So let's say that we were masking, let's say we're masking have, cat, and which is like one. So how many tokens do we have? 1, 2, 3, 4, 5, 6, 7, 8. So out of 8 tokens, we are masking 3 tokens, and then so they're replaced by. So I'm sorry. Of course, I will have its corresponding embedding. Have will have a corresponding embedding. Each word will have a corresponding embedding. But when you mask stuff, when you mask a word, then you no longer use that corresponding embedding. You have a special token called masked token. So they will be, so when you embed, it'll be like I here, but it'll be mask. And then A, it'll be mask. And mask, dog, end of sentence. So they will be, each token will be transformed to its corresponding embedding, and then you put this into the transformer encoder. So there's a gigantic transformer here, and then you put this into, of course, with the positional embedding inside added to each token, and then it'll be like, I don't know, 6 blocks, like 6 blocks of self-attention, maybe 12 blocks of self-attention. Let me see actually how many blocks there are. I guess they don't explicitly tell. All right, let's forget about it. All right. Anyway, so moving on. So you put this into the transformer encoder block, transformer. Let's say maybe 6 blocks. No, 12 blocks. 12. And then obviously the same number of output tokens will be generated from the transformer. So there will be here 1, 2, 3, 4, 5, 6, 7, and 8. And these were the masked tokens here, right? They are the corresponding output tokens. And they are the output tokens corresponding to the masked tokens from the input. So what you do is you take these 1, 2, 3, and then you try to predict the identity of this output token. So obviously this will be like I, this will be A, and this will be end, this will be a dog, and this will be end of sentence. They'll not exactly be like that, but because everything will be mixed and matched, and self-attention all coming together and convoluted inside, but still they'll relatively still maintain its identity. So it will be interesting to force this to predict. What would be the identity of this masked output? It should of course be have. And what is the identity of this masked output? It should be cat. And of course, this one should be A. So that is basically the training objective of Bert. And there is, of course, you can extend it to have another, there's one sentence here. I'm sorry. Because you want to use Bert model, the pre-trained model, in the downstream case where you need to translate one sentence to another, or you want to do question answering, where you have a sequence of where you have a lot of where you have a sentence on that, where you have a given sentence and a question sentence, and you want to predict the answer to the question. A lot of cases, you need to have 2 input channels, two sentences fed into the Bert model. So that's why sometimes you have one sentence here and the sentence separator here, another sentence, and you put the entire thing into the Bert, and then and you have the corresponding number of tokens here, and here. But that's the extension of the essence of the Bert. The essence of the Bert is that masked language model, which is what I'm which is what I'm describing right now. So like taking the masked output token and predicting its true identity is the essence of masked language model. So you can already see there's kind of it's a vastly different approach to GPT-1, which is GPT-1 was a good old language model. It just moves from it just operates from left to right only. But here, everything is, there's no masked self-attention. Everything is coming together like this, and everything is just attending. Like it's just complete self-attention. What like one token attending to all the other, and another token attending to all the other, and so on and so forth. So it's just like complete mess inside transformer. And since these masked outputs are already containing the semantic, well, hopefully some information coming from the unmasked tokens like I, A, and dog, and end of sentence, because they will already contain those information. So you can hopefully, you can hope that even though you don't know the identity of have or cat or you can still try to predict have, cat, and So that's the essence of masked language model. So, and you can see that why they call it bidirectional, because it's not moving from like this in this direction or in this direction. It's just everything is just self-attending to all the other every other tokens. So it's just complete, it's just complete like, yeah, it's a complete like set like it, yeah, it's even better than RNN basically. Just, yeah. All right, so yeah, you do this for a lot of time. You randomly mask a certain portion of your sentence. Yeah, okay, so you can see that why it is called bidirectional, and you do so every time you take a sentence, you randomly mask a certain number of subset of tokens to a mask token, and then you push it through transformer. You push it through transformer, and then you get the output tokens, and then you try to predict the true identity of the mask tokens. And usually people mask like 15% of your input tokens. So input sentence. So if for example, if your sentence is like 20 tokens long, then you mask out like three of them, something like that. And of course you can play around with it, like you can do 15%, 20%, 25%. I don't think it really matters as long as you just use like a reasonable number. So but the essence is that you need to randomly mask it and then try to predict this identity. And as I said, people use Bert. I mean, this is not the end of Bert, because you obviously, after you pre-trained like this for like a lot of time, a long time with a like humongous gigantic volume of data, you want to use this pre-trained Bert model in the downstream task, which can be like document classification or sentiment analysis, question answering, or whatever. So, and as I said, if for example, if you want to fine-tune your Bert model for a squad dataset, which is a question answering, then how squad works is that each sample in squad consists of a paragraph and a question, and you need to select a span or like a subset of the paragraph to indicate the answer to the question. It's like solving 수능 언어 영역. Like just to illustrate, like in squad, there's a paragraph of like facts, and then the sentence, and then there's like a question sentence here, like question, and then given this pair, what you need to do is you need to select a subset of a subset of a sentence in the given sentence to indicate the answer, like this. That's basically how squad works. So for example, like maybe this paragraph could be about the story of Martin Luther King or something like that. And then the question could be like, when did, like, how did Martin Luther King die? And then somewhere in the paragraph there will be like Martin Luther King was shot by someone, and then you need to select that particular sentence or particular like a sequence of tokens that indicate that, that potentially can be the answer to that question, something like that. So in order to do this, then you need to put both this paragraph and the question into the Bert, so that the Bert can, like, Bert can answer the question. So that's why I said, like, most of, like, Bert, actually you can extend Bert to have two sentences as input with a sentence separator in the middle. And then when you do this, then you can, like, you can mask certain portion of this sentence and mask a certain portion of this sentence, so that you can, like, try to identify, predict the true identity of the mask tokens. And also what you can do is there's another second objective function, which is next sentence prediction, or I think, or was it neighboring sentence prediction? Give me just a second. Yeah, there's next sentence prediction here. Next sentence prediction. So masked LM is what I described so far, trying to, like, masking random like 15% and then trying to predict its identity. Next sentence prediction is given given these two sentences, are they actually, like, consecutive sentences? So it's kind of like trying to capture the semantic meaning of the sentence, so that, like if certain sentence comes after another sentence, then they're like, there should be like a flow of semantic, or like for example, if the first sentence is talking about dog and the second sentence suddenly talking about, like, cars or tanks, then something is wrong there. So basically that's what next sentence prediction is trying to do. Like, sometimes you intentionally give a completely random sentence after the sentence, so that, and then you ask the Bert to, like, in the pre-training phase, you ask the Bert whether like this sentence is actually the true next sentence of this sentence, and, like, something like that, basically. Anyway, so I'm just skipping over the detail, because next sentence prediction is not really, it turns out it's not really impactful. Like, masked language model is what really makes everything works in Bert. Next sentence prediction is not so much. You can do it. It doesn't really matter whether you do next sentence prediction or not. The important thing is masked language model. All right. So when you pre-train your Bert model like this, let me just erase everything. When you pre-train your Bert model like this, yeah, here there's a good illustration. So there's sentence 1, my dog is cute, and sentence 2, he likes to play. He likes playing. I'm sorry, playing. So they're just, cutting playing into play and ing. It's like some like word splitting scheme. So there's a sentence separator here, and basically what you would do is you would, you can mask this one out and then mask this one out, and then try to predict, like, whether this should be a dog or whether, like, the true identity is ing. And here, there's a special token here, which is CLS token. What this is used for is when you have a downstream task that, that needs to work on the entire sentence level, like when you want to predict, when you want to do a sentimental analysis given the sentence, like whether the sentence is a positive sentence or a negative sentence, then having individual token is not really helpful. You need to have a token, you need to have a fixed size vector that represents the entire sentence, and that's what CLS token is for. So you have the CLS token that is used in the downstream task as a representation vector for the entire sentence. So when you want to do sentiment analysis, then you just take this token and then do, like, positive or negative in the downstream task, basically. All right, so interestingly, when you do this, suddenly everything is state-of-the-art performance. You can see that this is the entire glue data. Yeah, this is glue test results. So there's OpenAI GPT. Compared to that, Bert base and Bert large outperforms on average like 79.6% and 82.1% compared to OpenAI GPT, which was already kind of good. But like but Bert is just just another level. And when you do this on Squad, which is the question answering data set, is there? Yeah, so human performance is 89%, and Bert large performance is 83%, which is just I would say subhuman. I mean, almost as good as clearly better than chimpanzees, because chimpanzees can't speak. I mean, probably a lot better than children, because I'm pretty sure that 85 when they were evaluating with human input on Squad, they probably recruited at least like adolescents or adults. So I would say Bert large 83.1% is way better than like 5-year-olds or 6-year-olds. And Squad 2.0, this is actually Squad 2.0, which is even harder than Squad 1.1. Squad 1.1, human performance was 91%, 91.2, and Bert large is 93.2, which is superhuman. But Squad 1.1 is a bit. It has some certain limitations. So Squad 2.0 is a bit more complicated and is a bit more realistic than 1.1. So here, still, human is outperforming, machine learning models. But I'm pretty sure they will, at some point in the near future, they will outperform humans. All right, so that was Bert, and we should probably move on to GPT-2. Is this? No, GPT-2. So GPT-2, the title is Language Models Are Unsupervised Multitask Learners. And the reason they call this is because, first of all, what they do is they dramatically increase the model size of GPT-1 from, as I said, I think GPT-1 was using how many parameters? Does it say? Here, model specification. They were using yeah, I'm not sure. I don't think they explicitly say. Let me search parameters. I don't think they say. So basically, it's 12 blocks of 12 layers of decoder-only transformer with mass self-attention. How large is Bert? Oh, they were still okay. Bert base was using 12 blocks. Okay, it's about the same. So 12 blocks of Bert transformer encoder with hidden size 768 with number of attention head 12, total parameters 110 million. I think it's about the same here. 768 dimension states, hidden dimensions, 12 attention heads, 12 layer decoder only. So it's the same as Bert base. Okay, Bert base, which is 110. Now so this was 1.5 billion, so that's 110. That's at least okay. So now they blow it up to 10 times. GPT-2 is 10 times larger than GPT-1. And the reason they call that language models are unsupervised multitask learning is because once they pre-train a 1.5 billion parameter transformer decoder model using only language models, and they show that that pre-trained language model, the gigantic language model, can perform multiple tasks with minimum fine-tuning. Or is it even zero-shot tuning? Actually, let me see. Yeah, they're using zero-shot tests. Okay, so they don't even like. So the fundamental difference between this GPT-2 and Bert is that once you've trained Bert, pre-trained Bert, you need to fine-tune Bert on downstream tasks, like whether it's document classification, whether it's sentiment analysis, whether it's translation or question answering. You need to still you need to add one layer. So let me show that where that layer goes actually. So yeah, here. Once you've pre-trained your BERT model here, then you need to add one more. For example, let's say that you're doing sentence classification, whether that sentence is positive or negative. Then you need to add one linear layer here that takes the CLS embedding, and then that actually does like binary classification, or maybe it could be softmax. So linear layer puts through a softmax, and then you have a cross-entry, but like some not negative log likelihood objective function. So and you don't just pre-train this part. I mean, you don't just train this part with the true labels. You pre-train the entire BERT model. So the entire BERT parameters are fine-tuned on each downstream tasks. But in the GPT-2, that doesn't happen. So in BERT, backpropagation, when you're fine-tuning your model on a downstream task, backpropagation happens from the top all the way to the bottom here. So the entire parameters of the BERT model is fine-tuned when you're doing fine-tuning on the downstream task. But GPT-2 doesn't have that. When you're applying GPT-2 on downstream tasks, the backpropagation doesn't happen. It just how they do it is actually very interesting. So they pre-train GPT-2, the humongous transformer decoder doing a language model, just repeatedly predicting the next word one at a time. They in order to do multiple downstream tasks, what they do is, let me see. I forgot. So I think Lambada, actually, there's probably a better. Yeah, here, translation. So okay, so they even take the language model that they trained, the gigantic GPT-2, and then they try to make it perform English to French translation without even training or without even updating the parameters of GPT-2. So how they do it is, they take GPT-2, the pre-trained language model, and then they prime it. They prompt. I mean, in order to actually do certain tests, you need to tell the model that you want GPT-2 to perform translation. Like, and then the way they do it is they condition the language model on the context of example pairs of format English sentence and phrases. So what they do is, let me just draw it right here. So you have a gigantic transformer model that is basically a language model, and then you've pre-trained it on a gigantic like web crawl corpus to do a language model, and then you want to use this transformer language. You want to use the GPT-2 model for a translation test, and in order to tell GPT-2 that I want you to do translation, the way they do it is that they feed one English sentence. So I am a student, one word at a time, and then they put this symbol here. So everything is a vector, is an embedding, and then they put this particular equal symbol, and then after that they have Je suis étudiant, like this. I forgot about the like termination symbol. There should be some termination symbol here as well. End of symbol. Like this, and then they put this into transformer like one at a time. Like put this here, 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 here. So, and the transformer will know that will register this information into its hidden layer, and then GPT-2 would register this information into its hidden layer, and then after that they put another English word, the new English word, the English word that we want it to be translated to French. For example, let's say I don't know, like I have a cat. I have a cat. End of sentence. And then they put this. And now after this, everything is now prediction. So here, this part, given all this entire thing, now that we can start to predict the next word, because that's what GPT-2 does. Given previous tokens, what should come after? What should be the next token? That's what language model is basically. So you can basically, by priming your GPT-2 like this, and then giving this as the last token, you can start to sample or predict the French word using GPT-2 without no fine tuning at all. There's no backpropagation happening or anything. You just register this priming, this pair of example, and then you can prompt GPT-2 to translate this particular English word into French word. So of course you can do it autoregressively, like auto-regressively. So you predict one word, one French word, and then you use this to predict the next French word, and then next French word, and next French word, until you sample end of symbol. And that's how they use GPT-2 for various downstream tasks without fine-tuning the model, without any backpropagation happening. They just give this kind of a Q sign to the GPT-2 to make it perform any downstream tasks. And surprisingly, it does perform to some extent, interestingly. So in the translation case, the score was only 5 BLU, which is just terrible compared to let me see. Summarization. Or I guess they don't actually show. They don't actually compare translation performance with state-of-the-art models because it's just so freaking low. But they do compare with all the other tasks, like for example summarization. So summarization, how they prime or how they give the Q sign to GPT-2 is that they just add this TLDR token as the Q token, and then they sample, they can in the same fashion they give the full sentence, and then they give TLDR, and then they give the summarization, the true ground, the actual summarization example. So the full sentence, TLDR, summarization, and then another full sentence, TLDR, and then start sampling here. Start sampling another full sentence, TLDR, and then they start sampling from here. Like what should be the summarization? It's just the way they did translation, and the summarization performance is, let's see. So the best performance is 32.75. This is Rouge score, so which is kind of similar to a blue score. So Rouge 1 score was 41.22, and GPT-2 without any hints Oh no, actually GPT-2 with using TLDR as the hint, 29.34%. So without a single backpropagation or single fine tuning, GPT-2 can show like reasonably a good performance. Is as good as sequence to sequence with attention, which is fully trained on. So see, this model here is trained on summarization samples, and GPT-2 is not trained at all. There is zero backpropagation happening, and the performance is quite comparable, which is just mind-blowing. Just by doing language model pre-training on a humongous gigantic model with like thousands of like gigantic volume of corpus, you can suddenly do summarization without any fine-tuning at all. I mean, this is just mind-blowing. So in GPT-2, some tasks were doable with zero shot like this without any fine-tuning. Some tasks not so much. Like summarization, it did show like pretty good performance, but translation not so much, like only 5 blue scores. So there were like ups and downs. So that's the gist of GPT-2. And if you go to the supplementary material, some examples are just just out there. Let me see if I can get a good example. Sorry, give me just a second. Yeah, I think this was the chosen example. Or is it? Give me just a second. Something related to NDs. Right here. So what is this task? This is, so they've taken, so they used GPT-2, the pre-trained model, language model, and given a prompt. So human wrote this, and then they told GPT-2 to finish this article, which can be any like news article or blog article, whatever. But basically, given a human cue, try to finish this article. That was what that's what the OpenAI people told GPT-2 to do. So, and this just the result is just shocking. Take a minute to look at it. So, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountain, which is obviously false, because unicorns are just imaginary animals. There's obviously no unicorns living in the Andes Mountain. But what we're trying to see here is that if we prime, or if we give this as a context, then would GPT-2 generate sentences or article that is consistent with the context? So, and even more surprising to the researchers was the fact that the unicorns spoke perfect English. These are all just perfectly. These are just purely false information. But we want to see if GPT-2 can take this information, digest it, and then generate a sensible sentence out of based on the context. So let us continue. So GPT-2 said the scientists named the population after their distinctive horn, because unicorns have horns, which is just mind-blowing. Ovid's unicorn. I don't know where Ovid comes from. These 4-horned silver white unicorns were previously unknown to science. Makes perfect sense. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. Dr. Jorge Perez, just random name, an evolutionary biologist from the University of La Paz, which is the capital of Bolivia. Is it La Paz. Capital Bolivia or Colombia? I'm not really sure. No, the capital of Colombia is Bogota, so probably it's Bolivia. Anyway, so some like Andes Mountains. So some country that that has Andes Mountains somewhere in the region has the capital named La Paz. I think it's Peru or no, Peru's capital is Lima. I'm sorry. So let's say Bolivia. So Bolivia is obviously near the Andes Mountains. So University of La Paz and Andes Mountain, again, very consistent. Surprising. La Paz and several companions were exploring the Andes Mountain, here, consistent, when they found a small valley with no other animals or humans. Perez noticed that the valley had what appeared to be a natural fountain surrounded by two peaks of rock and silver cell. Perez and the others then ventured further into the valley. By the time we reached the top of one peak, the water looked blue with some crystals on top, said Perez. So everything, like Perez, it's all consistent. Like the same name is used consistently. All right, I'm gonna clear the scribbles. Right here, Perez and his friends were astonished to see the unicorn herd. Again, it's the same like consistent theme. These creatures could be seen from the air without having to move too much to see them. They were so close they could touch their horns, still the horns. While examining these bizarre creatures, the scientists discovered that the creatures also spoke some fairly regular English. Again, because at the top, they spoke perfect English. So the GPT-2 model is memorizing the context, the fact that was indicated by the context, and it is using that fact and when it's generating the downstream sentence. Perez stated, we can see, for example, that they have a common language, something like a dialect or a dialectic. That, yeah. Anyway, so yeah, it's just the entire article just makes perfect sense, which is, of course, I mean, openly I might have cherry-picked this like grand example, the prime like champion example, but still, even so, it's just like, like clear indication of what large models can do. And maybe like, I think they put this in their blogs or their GitHub or whatever, but they say that they, this explain the potential risk of this kind of like gigantic language model, because maybe I think they use the example like where the terrorists can use this language model to generate like propagandas or like ideological, some to promote their ideology or like their violent acts or whatever, or maybe some radical I forgot what. Give me a second. Yeah, radical religion. Sorry, that word somehow escaped. All right. Yeah, radical religion or like fundamentalists or extremists might be able to use this, language model to, generate like infinite amount of propaganda or articles or tweets or whatever, because basically it's free. There's like almost zero labor going, required to generate this kind of high quality article using GPT-2. So they use this kind of, they explicitly say certain risks or like potential risks of developing such open sourcing this kind of like high quality language model. All right, so we're almost probably out of time, so we're going to move to the last one, which is GPT-3, which is even larger than GPT-2. I'm just going to skim over it, actually. So GPT-2, as I said, GPT-2 is using 1.5 billion parameters here. 1.5 here, 1.5 billion parameters. And now GPT-3 is using, I mean, the number of pages is just, it's 63 pages long. It is using 175 billion parameters. So it's at least like 170 times larger than GPT-1. So GPT-2. So GPT-2 was using 1.3 billion 1.5 billion, but let's say 1.3. So what is described here is that it is still the same thing. It's a they pre-train GPT-3, which is way bigger than GPT-2, using the same language model objective function, and then they apply it to downstream tasks without any fine-tuning, without zero backprops or weight updates, just the same, priming or giving the Q sign. It's the same setup. Just everything is the same except for the size of the model. That's the only difference. But that's what makes all the difference in the world. So, and zero shot. So what they distinguish between zero shot environment, one shot environment, few shot environment. So few shot environment is when, for example, when they do translation, they give several English equal French pairs, like maybe 3 pairs or 5 pairs or 10 pairs. Zero shot is giving 0 pairs. One shot is giving 1 pair. Few shot is giving like at least like 5 or 10 pairs. So giving few shot is probably way more reasonable because you want to tell GPT-3 what kind of task we want it to do. So if you want GPT-3 to do like translation tasks, then we want to show at least some number of examples to correct examples to guide, to tell what we want it to do. So, and when you use few shot environment, then using 175 billion parameters shows way better performance compared to when you using 1.3 billion parameters. I mean, it's just just mind blowing. All right, let's just dive directly into the experiment section. Yeah, look at the number of parameters here. Like it's using 96 self-attention blocks, 96 self-attention blocks, and the hidden size is, remember that GPT-1 was using 76 8-dimensional hidden layer. Now it's using 12,000 dimensional hidden layer, and the number of multi-head attention is 96, and the dimensionality of the attention head is 128, which is not that large actually. And the batch size, it's, so before it was using 5,000 sentences per batch. Now I'm sorry, not 5,000. It's using batch size 500,000. I'm sorry, I can't really comprehend 500,000 batch size. What does that mean? Does it mean 500,000 tokens? I think, yeah, that should make sense. I think when they say batch sizes, they probably mean the number of tokens used per batch. Okay, so yeah, batch size and tokens right here. Batch size and tokens. So if they're saying that 500K tokens, that means how many sentences? Let's say that each sentence consists of 100 tokens, then 500,000 is 5. Okay, so they're using at least 5,000 sentences per batch, but now it's 6 times larger. They're using 3.2 million tokens per batch, and the learning rate is quite small. I mean, imagine the engineering effort put into GPT-3. There's possibly no way you can fit a 175 billion parameter model into a single GPU, which is just out of the question, just impossible. So they probably divided into several, maybe not several, maybe like, I don't know, dozens of GPUs or maybe hundreds of GPUs. I'm not really sure. I can't really imagine the amount of engineering effort put into this project. All right, so moving on to the experiment section. Total compute used during training. Imagine how much computational resources you need to basically waste in order to train a 175 billion parameter model. Like, think of the electricity consumption, the power consumption of this model. It's just like, is it really worth it? I'm not really sure. They probably use like same amount of electrical energy used in a small town in during the entire year, something like that. But science is science. All right, so let's see. What is this? So Lambada test, I think it's it's a long-range dependency in text. So given a long sentence, you are supposed to fill in, predict the last token, the last word in the sentence. That's Lambada test. So it's very context dependent. The model really needs to understand semantics to actually precisely predict the last word and last word only. So that's Lambada test. And you can see that GPT-3, so previous state-of-the-art Lambada model was showing 68% accuracy and 8.63% perplexity. And GPT-3 few-shot is actually outperforming the state-of-the-art model by a significant margin, and also perplexity significant margin. It's just mind-blowing. It's not even doing, it's not updating its weights or fine-tuning on the Lambada dataset. It's just, all they did is they just took a gigantic model and pre-trained it for using the language modeling objective function, and then they just gave a few correct examples of Lambada, and then made the GPT-3 perform Lambada, and it's outperforming the state of the art by a significant margin. That's just unbelievable. And several other tasks, story close, hella, so I don't know what they are, but still, like state of the art and the GPT-3 few-shot, there's the performance gap is narrow enough in my estimation. And let's see some other tasks. 3 open domain QA tasks. Open domain QA, so open domain question answering. So T5 is what used to be the best, no, not the best, the biggest model before GPT-3. So T5 comes from Google, obviously, and it is using 11 billion parameters, and it's just stupidly large model with humongous number of pre-training time, a lot of time spent on pre-training, and it was showing state-of-the-art performance on a lot of things, and so it's open domain QA tasks. And when they say open domain, the RAG model is actually using Google search engine to perform QA tests. So QA tests, so which is, you can think of this as the upper bound performance when actively using a search engine while trying to answer your question. So closed book is a bit more realistic. So closed book test is you just take the model and then you force the model to answer the question. So the model already needs to contain a lot of common knowledge in the model to begin with. And prior to GPT-3, T5 is the best model, as I said, and it is showing a pretty good performance on three question answering data sets. So like here, but GPT-3 with few-shot environment, it is outperforming even the previous state-of-the-art model using Google search engine while it is inferencing. It is outperforming that on Trivia QA. Of course, other models, other data sets, not so much. Not so much, but still, on Trivia QA, it is outperforming even the state-of-the-art actively using Google search engine. So again, it's just mind-blowing how GPT-3 can do that. It is probably because GPT-3 was trained on like a gigantic corpus crawled from the web. It is containing a lot of common knowledge coming from the web. So it is probably, that's why it can answer a lot of questions with ease. Again, a lot of impressive results following. And translation, can they do better than before? Remember that in GPT-2, translation was showing that for French English or English French translation, the blue score was 5. So they didn't really compare with the state-of-the-art model. But now, in the few-shot environment, state-of-the-art English to French was 45.6. Blue, there's a blue, 5, 5 blue. So they're using blue score, and now actually let me see. Yes, I'm sorry. So yeah, so so the state of the art is obviously supervised. So when I say supervised, the state of the art models are trained to do this and trained to do this and trained to do this. English to German, German to English, English to is it Russian? Something like that. Anyway, so and these are unsupervised models or fine-tuned models. I'm sorry. Is it unsupervised or fine-tuned? Let me see. I'm sorry, I'm not really sure because I don't really know all the details of this model, but it is already impressive enough because state-of-the-art model solely trained to translate French into English was showing 35 BLEU score, but GPT-3 Few-Shot is actually outperforming that without even a single weight update or any fine-tuning, which is just mind-blowing. Again, here it is almost as the same as the state of the art, and as the a caption says, it is specifically showing strength when translating to English. So when translating into English, like French to English, German to English, or Russian to English, that's when GPT-3 actually outperforms state of the art. Compared to that, conversely, like when translating English to French or English to German or English to Russian, not so much, because obviously GPT-3 was trained on English web crawl corpus, so it has way more strength in language modeling or predicting English words compared to predicting French words. But still, it's mind-blowing. Like trying to generate French words, French sentence from English sentence, it is doing a pretty good job, even though the entire GPT-3 was trained on English web crawl corpus mostly. So it's just mind-blowing again. So again, yeah, a lot of results follow. Do they have squad? They do have squad. So squad 2, fine-tuned soda is 93%, GPT-3 Few-Shot 70%. So there's still some room to actually catch up to fill in. And yeah. And let me just show one final example before I finish this class. Yeah, this was one of the most interesting examples. So what this task is, they define a word that has never seen before, by like completely fake word, like here, what poo. So what this game is, the user defines a new word and gives an example how the word is used in a sentence, and we want the GPT-3 to do exactly that. So this is because this is a one-shot example, or is it few-shot example? I'm not really sure. Anyway, so it is giving some correct examples to prime or to give the Q sign to the GPT-3 before we want it to actually do the task. So, for example, here, a watpu is a small, furry animal native to Tanzania, which is completely false. There is no animal called watpu. An example of a sentence that uses the word watpu is, we were traveling in Africa when we saw these very cute watpus, because watpus are supposed to live in Tanzania, which is an African country. So that this sentence is a correct sentence, assuming that this is a correct definition, of course, which is completely false. So this is just a game to see if the model can understand language. Again, all right. The next example: to do a fardodal, means to jump up and down really fast. An example of a sentence that uses the word fardaddle is, that is the cue. And we want the model to generate the sentence, and the model generated this sentence here. One day when I was playing tag with my little sister, she got really excited and she started doing these crazy fardaddles. And it's totally making sense. Because fardaddle means to jump up and down really fast, and they were playing tag, which is 술래잡기 in Korean. They were playing tag, and then she got really excited and started doing these crazy fardaddle. That means that GPT-3 completely understands what the user wants it to do using the completely new word fardaddle, which doesn't even exist in English. Yalubalu is a type of vegetable that looks like a big pumpkin. An example of a sentence that uses the word yalubalu is, now this is a generated sentence from GPT-3. I was on a trip to Africa and I tried this yalubalu vegetable that was grown in the garden there. It was delicious. This is just crazy because, again, yalubalu is a big pumpkin, and that's it. Yalubalu is a type of vegetable that looks like a big pumpkin. It doesn't say anything about the origin or the region that it is grown or anything, but it says that GPT-3 somehow thinks that it is natural to generate a sentence where the subject goes on a trip to the Africa and try this yalubalu vegetable. It was grown in a garden there. It was delicious, and it just understands that the vegetables are grown in a garden. It already understands that fact, and to me the most mind-blowing thing is that yalubalu somehow, I don't know, somehow sounds like an African word, doesn't it? Yalubalu sounds like an African word to me, like bubuzela or whatever. And I think that's why GPT-3 intentionally injected the word Africa, trip to Africa, in this sentence, because yalubalu sounds like something that has connection to Africa. I think that's why GPT chose Africa in its example. And if that's true, then it's just, probably better than most humans. All right, I'm gonna stop here. I've already taken up too much time. All right, so GPT-3 using 175 billion parameters, it's just showing mind-blowing zero-shot or few-shot learning capabilities. And I think there is still a lot more way to go, because what would happen if we use like 1 trillion parameters? Nobody can really answer. And Bert can probably go about the same way. Just train a Bert model with 175 billion parameters, and let's see how it goes. Nobody really knows. Nobody really can imagine what the outcome would be. So I think there's a lot more potential to this. Unfortunately, sadly, schools can probably not do this. Maybe there's only 2 companies in the world, or maybe 4 or 5 companies in the world that can actually realize this vision. Google, OpenAI, Amazon, and maybe Facebook. I don't know. So yeah, it's an exciting time and a sad time at the same time for machine learning researchers these days. All right, I'm really gonna end now. So I would like to thank all the attendees, all the students and the neighbor engineers for participating in this class and sticking to the very last class. I hope it was really helpful to a lot of people, and I hope that it was. I tried to keep it as interesting as possible, and I hope I pulled it off. So, all right, thanks for participating, being part of this course for the entire semester. I hope I can see a lot of you again in the future, and yeah, take care, and hope you guys can stay relatively interested in machine learning for healthcare for a long time in the future. All right, bye bye. Thanks.